Hello, everyone. This video will talk about an equiprobable space. So this is the simplest kind of probability assignment. So um, a probability assignment is equiprobable, is an equiprobable assignment if on S, and remember S is our sample set, our sample space, O's, these are our outcomes, and we have capital N of these. If, when we make the probability of a single any outcome, we get exactly 1 over N. So in other words, each outcome is equally likely to happen. That's the idea of equiprobable, is that all of the probabilities are equal. So it's in the name of the assignment. Okay, so many probability assignments that happen with sort of a finite set of outcomes are equiprobable. But most of them assume some kind of a fairness. So let's take a look. Before we take a look at an example, actually, let's take uh, make an observation on what the probability of an event is. So in this case, if an event E has, say, K outcomes, in other words, remember events are subsets of our sample space, then when we try to find the probability of the event, well, we just take this is equal to the sum of the probabilities of each of the outcomes. But those probabilities, since we're dealing with an equiprobable space, are 1 over n. So we have k of them, and they're each of probability 1 over n. We add them up, we'll get k over n. So this tells us how we can easily compute the probability of any given event, assuming we can do a good job counting the number of outcomes in that particular event. This is very useful, very powerful, and let's take a look at an example here. So here's an example of a fair coin toss 3 times. And we've seen before that we can indicate the sample space by just writing a sequence of the outcomes of each of the tosses. So tails, tails, tails would be this one. This one is heads, tails, heads. Okay, so this is our sample space, and we recognize that n in this case is the number of outcomes is 8. There are 8 possible outcomes here. So we can ask for the probability of any given outcome. And in this case, I mean, it's a fair coin. So that means that it has equal probability of happening each time as a heads or a tails. So there's no preference really of one happening over the other, of any one of these outcomes happening over the other. So in particular, the probability of any outcome, I'll just say, oh, this is equal to 1 over 8, no matter what the outcome is. And then you can ask all kinds of simple questions like, what is the probability of 1 heads coming up? Exactly 1 heads. So I'll say, yeah, I'll say 1 head. But one of the tosses is a head. Exactly. Well, there's only 3 of those, right? This one, and this one. So I can write this down as probability of, I'll just say heads, tails, tails, oops, tails, heads, tails, and tails, tails, heads. And since there are three of them, we can use this formula here to say that this is 3/8. So we just take the number of outcomes and we divide by the total number of the number of outcomes in our event, and we divide by the total number of outcomes um, in the sample space. So on the other hand, here I'm going to move this down. I got a little bit ahead of myself here. I could ask maybe three more questions. I could ask, what's the probability of no heads? I could ask the probability of two heads. And I could ask the probability of all three of them being heads. And what happens is you are sort of partitioning your set into a bunch of events in this case. So no heads, there's only one. This is a simple event. There's only one outcome here. And so this is 1/8. Two heads, well, we can write them out. There's a heads, heads, tails, heads, tails, heads, and tails, heads, heads. And again, this is 3/8. And this is three heads. There's another simple case. This is heads, heads, heads. And so this is 1/8. And again, all you're doing to go from this line to this number is you're just counting up the number of outcomes and you're dividing in the event and you're dividing by the total number of outcomes using, again, this formula. All right. Very good. Another example that's really fun to kind of play with is rolling a pair of dice. And so here we are taking what the book did. We're just doing a red die and a blue and a black die, and we're rolling, this pair. And I've written out the sample space. And again, there's no assuming that the die are fair. In other words, they're not weighted in some way. There's each one of these outcomes has equal probability of any other of the outcomes. So again, this is an equiprobable space. And you can ask all kinds of questions here about what the probability of a given event is. So in particular, the probability of a particular outcome, in this case, because there are 36 possible outcomes, is 1/36. So using this, maybe using the fact that, or I should say, n is equal to 36, as we've seen, we can ask some questions. So for example, we can ask, what is the probability? I remember we talked about the event of landing on free parking if you're starting uh, on visiting jail in Monopoly, you want to roll a 10. So what is the probability of rolling a 10? And for that, we are just going to take the probability of the event rolling a 10, and we need to just write down what that event is. What are all of the outcomes that give us a 10? Well, we can go ahead and select them. We can get a 6/4. That's one possibility. We can get a 5/5. That's another possibility. Oops. Or we can get a 4/6. That's another possibility. But those are the only possibilities. And so this is our mathematical event. And we can then calculate it by saying, okay, well, n is 36. It's an equiprobable space. In order to calculate this probability, I just take the number of outcomes in the event, I divide by the total number of outcomes. So 3 divided by 36, or 3 over 36, is 1/12. So there's a 1 in 12 chance that you're going to land on free parking. Not too bad, but not too great. So this is how a probability will work in an equiprobable space. Now, there are some tricks that you can use when you're trying to calculate probabilities just generally, but often are used in equiprobable spaces when you have a hard time counting the number of outcomes in a given event. So then this is some vocab. So let me write down vocabulary. One thing to keep in mind are complementary spaces. So are complementary events. So two events are called complementary. Let's give them names. E and F are complementary. Sorry, it's complementary. If uh, if all outcomes are either in E or F, but not both. Either in E, I shouldn't say all, let me say if any outcome is either in E or F, but not both. In other words, the two outcomes or the two events break up all outcomes into two separate sets. So an example of complementary, so this is one vocab word to keep in mind, complementary events. An example of this would be, you know, uh, rolling an even and rolling an odd. So example, E is rolling an even, and F would be rolling an odd number. And by rolling a number, I mean you add up both of the red die value and the black die value, and you get a number. So when you roll the two die, you're going to be in one situation or the other, but not both. Okay. So now, when two events, when E and F are complementary, you can observe that the probability of one of the events is one minus the probability of the other. So how do you see that? Well, the probability of E happening, either an outcome is going to be happening in the event E, or an outcome is going to happen in the event F, but an outcome will always happen. So the probability of E plus the probability of F is 1. So another way of saying this is the probability of rolling an even is 1/2, as is the probability of rolling an odd. So adding these numbers up will give you 1. All right, another vocabulary item to keep in mind is the notion of independent events. And this is can be a kind of a tricky notion. So, and you should completely, these are not very different notions. So the complementary events is very different than the notion of independent events. So two events, E and F, are called independent if The probability, or if the occurrence of one event does not affect the probability of the other. So let's give an example of this, and then we'll state a result that's really useful for independent events. And independent events are very nice when you have them, but not always occurring. So um, let's do an example. So an example of two independent events would be um, the black. So we'll use this dice example. So the black, uh, so E is the black die is even, and F is the red die is 6. Okay, so these two events are completely independent because the whatever the black die is, it doesn't affect the probability of what the red die is. So more formally speaking, we can look and say, okay, well, what is the probability of F happening? Well, let's go up and we'll bring this down and make an easier computation of it. So bringing this down, we can make these computations. So the probability of F is 1 in 6, right? The red die is 6 in all of these guys. So there are 6 possible events and or 6 possible outcomes in this event. And there's 36 total outcomes. So this is 1 over 6. Okay, so that's the probability of F happening. Now suppose, now let's take a look and say that E happens. So let's suppose that E happens. The black die is even. So if the black die is even, we can go ahead and figure out what that event is. Let's just find out what the black die is even is. Instead of thinking about the sample space, I'll think about the event E. Well, if the black die is even, that means that we're in an even row. So I can get rid of all of these. I can get rid of all of these. I can get rid of all of these. Hope I can get rid of all of these. Okay, great. And now, what do I have left? Well, I have all of the outcomes that live in E. And now I can ask what is the probability of F occurring now? Okay, in other words, now I have a new probability space, and that's the probability space of E. And within that probability space, I have F happening, right? This is where the red die is 6. So E has how many? 3 times 6 possibilities. So E has 18 possibilities, 3 times 6. And everything is equally possible now because E has occurred. So we're in this situation. And now the number of possibilities in E and F, this is, maybe I'll write it as E and F. This is 3. So then the probability, using an equiprobable assignment, as we should here, of E and F is equal to 3 over 18, which is 1/6. And that is the same number as the probability of F happening on its own. So what we're saying here is that the effect of E happening did not affect the probability of F happening. So if E didn't happen, F had the same probability as if E did happen. That is what it means for these two events to be independent. So E and F are independent events. Okay, let's give another sort of counter example. Let's do the free parking. E is, maybe counter is the wrong word here, maybe a non-example or something. E is the case where we get to free parking. So we roll a 10. And F is again roll a 6. Um, sorry, F is the red die, roll a 6 with the red. The red die. Okay, so we've calculated the probability of F altogether happening is 1 over 6. That's the same as what we just did. But now let's look at what happens when we try to do what we just did, but now we have E happening. So E is just, let's suppose E happens, then what we know is that we're in this situation where one of these three things has happened here. Either we've gotten 6 and a 4, to move this over, a 4 and a 6, or let me go up and grab this one, a 5 and a 5. So these were the three possibilities for E for rolling a 10. And now we look and we say, within this, when is F happening? The six is rolled as for the red die. Okay, well, there's only one case where this is F, and this is F and E happens right here. So assuming E has happened, this is what's called a conditional probability, but we're not going to talk too much about that here. Assuming that E has happened, we can see that the probability of E and F with E happening, this is equal to 1 out of 3, because this is the only outcome. So what we see here is that these two things, these two probabilities, they're not equal. And when they're not equal, they are not independent events. So E and F, in this case, are not independent. There's a higher likelihood that the red die is a 6 if you know that you've rolled the dice and gotten a 10. All right. So what can I say, and as one of the last things to say for this video about independent events? Why are they so useful? So let's just say why a fact about independent events is that if I want to know the probability of, so I should say, let's assume they're independent. So let's assume E and F are independent. Events. And if I assume that if I assume that E and F are independent events, then the probability of E and F both happening is equal to the product of the probabilities of E and the probability of F. So that is very useful in many different cases. And indeed, we could just verify this with this example up here. So here I kind of miswrote probability of E and F. I'm saying probability of E happening and then E and F happening. Okay. So let me correct that for the record. But now what I want to say is, what is the probability of E and F happening within the original sample space? Well, the probability of E and F happening here is this this probability. So this is the case where uh, we have that the red die is 6 and the black die is even. And you can see that that's 3. There are 3 possible events there. So in this case, I'll write this over here of E and F. This is going to equal exactly 3 over 36, right? Because there were 36 original events. The probability of F we calculated. The probability of E, well, we saw that there were 18 of them. So the probability of E is 18 over 36. 18 over 36, if I divide by 6, is 3 over 6. And so what you can see is that this is equal to 1 over 6 times 3 over 6, but that's equal to the probability of F times the probability of E, as we wrote before. So what am I trying to say? Saying that the probability of both of these events occurring is equal to the probability, the product of the probabilities of the events. Now, this happens under the assumption that these are independent events. If they are not independent events, this is just nonsense. So really, that's something that you don't want to use this equation unless you know that the events are independent. Okay.